Hi, I'm Savannah, and I assume you know Bruce. We are giving this talk together, and in true Gig City fashion, we're going to take you on an expedition. And we're going to start by telling you a story. It's a climber story, but it's also a machine learning story. And strangely enough, it's not a Python story, it's an Elixir story. So we're going to either look at the photo on the screen, or you can close your eyes, but we're going to set a scene. You're going to imagine yourself in the breathtaking Bugaboo Provincial Park in British Columbia, Canada. You're perched 1,100 feet above the ground on the sheer face of a granite spire. Your objective is clear: to ascend the 1,800-foot, 16-pitch route to the summit. This isn't just a simple trek up the mountain. You're engaging in a challenging rock climb, leveraging your expertise and a selection of sophisticated climbing gear. Picture that in the early stages of your climb, a mishap happens and causes you to lose all of your food supplies. Fatigue sets in by the 10th pitch, making each move a test of willpower with only a small snack since dawn to sustain you. Yet you face 6 more demanding pitches and an arduous descent before you can even think about the A&W burger down the road. End scene. Okay, so I highly doubt you found yourself in this situation. This is actually from one of my trips in 2019. And if you couldn't tell from my very professional speaker photo, I really like to climb rocks. And while I love to tell you about my adventures in the mountains, I recognize that you're not all aspiring alpinists and are waiting for the part where I relate this back to Elixir, so it's coming. Let's talk about what climbing and machine learning Elixir have in common. To do this, I'm going to show you one of the most famous and famously bad acronyms of all time. It's really awesome. Do you know where I'm going with this? Awesome? Yeah. Anyone who took a data science class got it. Awesome stands for obtain, scrub, explore, model, and interpret. Yeah. We want to walk you through these in the context of a climbing expedition. And these are the Elixir machine learning projects we're going to talk about today. It's going to be Livebook, NX, Axon, Bumblebee. The first letter of the acronym we have baked into Elixir, obtain. Elixir is really great at this, getting, moving, crunching data concurrently and efficiently. And looking back on my trip, I can see that the data science process was a lot like how we planned and executed our trip. On my climbing adventure, we spent a good amount of time planning and eventually arrived with the decision to climb this route. It's called Minotaur Direct, and it was established in 2016, which makes it a relatively new route, and it can be free climbed with traditional climbing gear. Does anybody climb in here? Anybody? Okay. So you guys have like a vague understanding of what I'm saying when I say traditional climbing gear. So I'm not gonna like go too much into the climber lingo. So yeah, I'm sorry if I lose you a bit, but our general plan was to hike in 3 hours, arrive at base camp, wake up the next morning, do a proper alpine start of 3 a.m.-ish, hike to the base, and then do this 16-pitch climb up and down in a single day. We obtain the rough details by referencing forums online and chatting with friends. Scrub is, in data science, is to remove problems in data and normalize. On the Elixir side, this usually happens not in the language, but in our editors, databases, and tools. For climbing, this meant pruning out the places we didn't want to go. There were other options that were too far away, too risky. This is actually from the summit of the route that we did, and there were other mountains in the back that we could have chosen, but we did not. The E is explore, which is explore data via charts and tabular data. Elixir is pretty inefficient at this, or at least it was until the data science team built Livebook. Now it's world-class. And I assume most of you are aware of what Livebook is, but if you're not, Livebook allows us to plan and test our code and applications in a nice, concise environment, and even has excellent neural network integrations, which we'll dive into later. In relation to our climbing expedition, we were able to complete a route and explore pretty wild terrain. And a huge reason we were able to do this is because of the innovations in climbing. And I'm going to give you just a really brief history in climbing to kind of explain what that means. This photo was taken in the early 1900s. It's of two women in dresses and loafers, and they don't even have harnesses on. They actually just have like the rope tied around their waist. And then I don't know if you can tell, but they have the rope like draped over a ledge. So if they fall, I don't know, I guess if the rope doesn't cut, then they'll die because their backs will, I don't know. It was really, really risky and inefficient back in the day, but people were a lot cooler back then and I guess didn't care. Yeah, so there's been a lot of advancements in climbing, just like in machine learning, and there's stuff like pitons, hooks, and modern day trad climbing gear that was created to not only make the sport safer, but it made it more possible for humans to do much more like harder and wilder terrain.
So Savannah got the climbing, the live book. I get the math. At least I don't have to follow Todd. So I want to talk a little bit about what Elixir it was coming into. But I don't want to provide too much about the basics of NX. What I'd like to talk about instead is what machine learning looks like. And then we'll talk just briefly about where Elixir snaps into these pieces. So if you look at that gray dotted line, that's the left half of the OSIM, the awesome. That is the obtain, scrub, and explore. So we already have data coming in at this point. And our goal now is to build a model that we can use to make predictions. And it's not surprising that that model is a function. And so now my job, since this is a 25-minute talk, is to give you a background of neural networks in 3 minutes. So a neural network is based on the idea of what our brains look like. It's neural, so it's made up of neurons, and in this case, the neurons are functions. So this is a function. And this is how I define it in Elixir, but what's interesting about this is this particular function is going to use scalar data. So that means that the inputs and the outputs are usually single mathematical entities, or floats or whatever. In machine learning, this is not what happens. The functions take something called a tensor, which is normally an array, a multi-dimensional array. And I said an array, not a list like Elixir, because we need random access across many dimensions to very large data. So rather than a def, this isn't a typo, we have something called a def-in. So I don't know if everybody remembers when Jose created the machine learning stack, but it was wild, right? So there was this odd silence, and then he started teasing it. He said, I've built this really fast thing, and everybody was wondering what that really fast thing could be. And it turns out that Jose had ripped out part of the type model and part of the numeric computation model of Elixir and replaced it, and did it with a combination of macros and other systems that he wired into with Elixir's tools for building such systems with macros and with behaviors and with other functions. So one of the cool things about NX is that when we're going to be working with tensors, we're going to use def-in, and so it's going to kick us into a different ecosystem, so that when we have an X, it might have multiple dimensions. Then we're going to take these tensors, and though this layer has single inputs, what's going to happen is that since we're working with multi-dimensional data, it's going to look more like a network or a mesh, right? So when you multiply one tensor by another one, you get a lot of inputs and a lot of outputs. And you can express that with something that looks like a pipe so that you have these different layers and you can connect them with simple algebraic functions. And it looks like a pipe in Elixir. And so the interesting thing is that if I stopped here and I was building something like a Zillow, then the only thing that I could do is, for example, if I was predicting the value of a house based on the square footage, I could only build a linear model, but that's not what we want to do. So in machine learning, what we do is we apply this thing called an activation function. And this activation function allows us to basically reproduce nonlinear outputs, right? So that's it. That's as much as I'm going to torture you about what a neural network is. So in summary, this is a model that's a neural network of neurons, which are functions that take tensors and are applied in layers that we connect and apply activation functions to make them nonlinear. Or if you want to simplify it a little bit, you could say a neural network is, there's a neural network of layers with tensors and an activation function, or big fat hairy function with pipes and custom nested lists that's replaced with something else that's efficient for random access, and some type of obfuscation function that that allows me to express nonlinear inputs. Okay, so initially our model is still a function, but before we train it, it basically presents random noise. So it's still something that can be used to build a prediction. It's just that the predictions are bad, right? And so what do? We improve this model by tweaking the constants step by step by step. So we take this data, we feed it into a model, and remember that model has inputs, but it also had constants that we multiply and add that we can change with the trainer a small step at a time until it makes not only a prediction, but the predictions that we want. Okay, sounds almost like science fiction, and it is. But this is what we're going to do. We're going to take a big blob of data that we produced with this Osman process, right? And we're going to cut it in half, feed roughly half or some chunk of it in. We're going to use that data to train the system. And then we're going to use the rest of the data to verify the system that we built. Okay? So what we're left with is a function that makes predictions so that if I have these left-hand side inputs, x1, 2, and 3, and we have these predictions, y1, 2, and 3, this is what it looks like. So we could look at this on a number line where you have the inputs and the predictions. But we start with an incomplete picture. If we had a complete picture, we wouldn't need a machine learning system. We could build a map or a function, right? So we're going to start with a subset, and we're going to train the system so that we can make guesses or predictions that get better and better as we train the system. So said another way, if I have this data, I'm going to try to build the best possible line between them. So where do I start? Strangely, I'm going to start with a random guess. Right? And then I'm going to have a function which is nothing more than a wrongness score, right? I feel like this wrongness score is most of my career, right? It's called loss, but it's basically a function of all those L's on the left-hand side. So here's an example of a loss function. It's just the sum of the square of all those distances, right? So if I tweak that slope, what's going to happen is I'm going to change the line one little bit at a time so that the losses get smaller. And if this line is too low, I'm going to tweak that bias and crank it up a little bit until the losses get smaller. So the name of the game here is to shrink the losses. So our optimizer actually works on that loss function, not the function that we just built, right? You make the loss small, you're good to go, right? And then once you do that, you can make a prediction. But remember, this is a boring prediction because it's on a line. What we want is something that's nonlinear. So we throw this other function at it called an activation function that lets us build more sophisticated curves. And that's it. Only thing that we're going to change is we're going to make this formula, instead of scalar inputs, we're going to feed tensors into it. And then we're going to add one layer after the next, right? So now I can build these nonlinear predictions. And in Axon, here's literally what this looks like. These are layers. It's just a pipe. And that's a tensor. And those are tensors. So we stack that input and we pipe it through the rest. This is literally a very simple Axon model. Now it's not fat enough because I don't have enough layers to do anything meaningful, but there's a FizzBuzz game predictor that is this plus 2 layers like it. And that's it. And you can throw data at it and it can learn to play FizzBuzz with nothing but this and the Axon models. So what does training it look like? Well, for a simple model, you could say, hey, this is going to be a simple process. Remember, if he's climbing up and the loss is getting higher and higher, that's not the goal. The goal is to make the loss smaller. So you just go down, right? It turns out that this is oddly complicated as the model gets more and more complex, as the domains get more complex, or even hopelessly complex, because it's hard to tell which way is down. So, this is what a complex model looks like. 96 layers. Training data that's 570 gigabytes. Training time of 355 GPU years. So what we're going to do to simplify this process is we're going to use some modern tools. And in machine learning, it used to be that if you have this sophisticated tool, then you were one of the best frameworks. But now it's table stakes, and I want to talk about what that tool is. But this is like the crux move for a machine learning framework, right? It's what's in the middle of everything. And Elixir's NX shipped with this capability. It's the crux move for NX, right? So we call the crux move for machine learning auto gradient, or auto differentiation. Another way is just to say it is just calculus. We're taking a slope of the loss curve, and then we're following it in the other direction. We go down. So all it is answers the question, which way is down? Or to answer it another way, we take one step in precisely the right direction that reduces my loss. And we do this over and over, even in complex system, and we have our answer. Okay, I promise, there's no more math. This is what the training model looks like in Axon. And that's it. Okay, Savannah, you want to take us home? She gets to do the fun part again.
So I don't know where to stand to not make that happen. You can pretty much ignore all of that because we have Bumblebee. Has anybody used Bumblebee? Raise your hand. Yeah, some of you? Cool. To talk about Bumblebee, we're also going to talk about our last letter, interpret, which the N is arguably a little forced in this acronym. And Bumblebee is awesome, no pun intended, because it means that we can leverage someone else's work. And it's not much of a stretch to relate this back to our climbing adventure, because back in 2016, a party of 3 ascended this route for the first time and equipped it with hardware, so it was easy to ascend and rappel in the future. And similarly, Bumblebee is leveraging a lot of people's work. And I wanted to just kind of show you a few demos that I really like to get up and running with Bumblebee. One of my favorites is Jose's initial Bumblebee talk. It's kind of like the hello world for Bumblebee. And he does the integration with Livebook and shows you how you can easily choose between different neural networks in a SmartCell tab and have predictions running in under 30 seconds. And then he also does like a really small embedded Phoenix application. How do I make this play? There we go. Yeah, he does like a little embedded Phoenix application and shows text to emotions. And all the code is essentially in 3 functions. It's really nice and concise. It's just if the model already exists, then we load it from Hugging Face, which is essentially the GitHub for datasets. We load the corresponding tokenizer. And finally, we utilize the text module text classification function to get our results. There's a bit of more with like index and stuff, but that's pretty much it for Bumblebee. It's super easy. I also really like Chris McCord's demos in general. He's just really good at talking and being really concise. But I like this video in particular because he has a speech-to-text module up and running in literally under 2 minutes. And the bulk of this video is honestly him fiddling with FFmpeg, but with the newest version of Bumblebee, you don't even need FFmpeg to chunk your content. So yeah, this video is really nice. He literally, just to show some of his code, again, it's like super small and concise. He ripped the code from the Bumblebee hex docs, plugs it in, and the biggest difference is that he's just using the audio module and obviously different models. And then the last one I wanted to highlight was Caitlin Burns' talk that she gave at the US Elixir conference. She really focuses more on eVision than Bumblebee, but there's a prediction component as well. But it's motion tracking and image identification. And I'm not going to talk about eVision really because there's just not enough time, but it's Elixir's implementation for OpenCV. But the entirety of this is done in 140 lines of code, which is pretty cool. Just like pure Elixir, 140 lines of code. And this is her project, which is pretty cool in my opinion. It's her on a trapeze, which felt appropriate for a climber talk to show some like trapeze stuff as well. But my favorite part about Bumblebee is that it is extensible. So if the model you need isn't implemented already, then you can just add it in, making Bumblebee an excellent addition to the Elixir machine learning toolkit. Okay, so I'm going to tell you how my climbing expedition ended. My partner and I, we actually did lose our food. There was a photo of me standing in like a red jacket with like this crevasse thingy. So all of our food fell down that because our bag ripped on the second pitch. And I think I'd only had like a Cliff Bar that morning or so. And so by pitch 10, I was feeling pretty bad. I was having a hard time staying awake in general. And I wanted to go down, but my partner wanted to continue, and he found Sudafed in our bag. So he took Sudafed on an empty stomach. I don't know if you've ever done that, but it's like consuming a bunch of caffeine. It's like taking a bunch of like caffeine pills on an empty stomach. So he was really excited. And he led the remaining 6 pitches, and I followed behind, and eventually I turned into that kid that like stayed up past their bedtime, you know, like whenever you like get really hyper. So like I got better. We finished the climb, descended the whole thing, made it back down, didn't have food at base camp, so that kind of sucked, but woke up the next morning and like beelined it out to A&W Burger. In total, our tent to tent time was around 20 hours, and 12 of that was actual on-the-wall time. Yeah, it was a fun time. While the actual climbing expedition probably seems a bit extreme, all of this was accessible because of the work of others, and similarly in Elixir, you can see how this relates. And we hope you enjoyed our expedition in machine learning. Neither Bruce or I are machine learning experts, but we wanted to show you that with modern techniques and tools, you don't have to be experts. But yeah, thanks. And here's the QR code for anyone who wants the links that we have. Oh, yeah. Yeah, he didn't know that I stuck that in at the last minute.